Right now, as you are watching this, the most expensive technological infrastructure ever built by human civilization is quietly becoming obsolete. The AI data center empire, worth over $1 trillion in active investment, is facing a threat it never saw coming. And that threat is not a better GPU, not a smarter chip, not a new cooling system. It is quantum computing, and what quantum just did in a lab in a single afternoon is something that would have taken the entire global network of AI data centers 10,000 years to complete. Let that sink in for a second. 10,000 years of classical computing power done in minutes. And if you think that does not affect you, personally, think again. Because the entire foundation of how the world builds and runs artificial intelligence is about to be ripped out from underneath it. Go ahead and hit that like button right now, because what you are about to hear is going to change how you see the technology world forever. And subscribe so you never miss the moments that actually matter. To understand why this is such a seismic event, you have to first understand what AI data centers actually are and why the world has been pouring money into them at a pace that has never been seen before in the entire history of private sector technology investment. These are not ordinary buildings with computers inside them. These are enormous, purpose-built, specially engineered facilities that consume as much electricity as entire countries. They are packed wall to wall with thousands of graphics processing units, better known as GPUs, which are the specialized chips that train and run large AI models every time you use an AI assistant. Every time a company processes AI-driven analytics, every time a new AI model learns from data, you are consuming compute power that lives inside one of these facilities, and the demand for that compute power has been growing so explosively that it has started to fracture the energy systems of entire nations and push electricity grids toward the edge of what they can handle. In 2025 alone, the world spent an estimated $580 billion globally on AI-focused data center infrastructure. The five largest technology hyperscalers in the world, Amazon, Alphabet, Microsoft, Meta, and Oracle, committed somewhere between $660 billion and $690 billion in capital expenditure in 2026, with roughly 75% of that money tied directly to AI infrastructure. That figure represents the largest single-cycle infrastructure investment in private sector history. Analysts at Morgan Stanley projected that large technology companies would commit more than $1 trillion in just the two-year window of 2025 and 2026 combined. $1 trillion spent on data centers to run AI, and nobody seriously slowed down to ask whether the underlying model that justified that spending had a ceiling. But here is the uncomfortable truth the people writing those checks did not want to confront publicly. The AI data center model was already beginning to fracture under its own weight long before quantum computing showed up. AI training compute requirements were doubling annually. The power required to run the leading AI supercomputer, Zeiss Colossus, grew from 13 megawatts in 2019 to 280 megawatts in 2025. That is more than 20 times the power consumption in just 6 years. Global data center electricity consumption reached between 460 and 490 terawatt hours in 2025, representing a 17% surge year over year against overall global electricity demand growth of just 3%, to put that in concrete terms that most people can feel. The AI data center industry was consuming electricity roughly equivalent to the entire annual electricity usage of France, and the International Energy Agency projected that by 2030, that number would double again to around 945 terawatt hours. The machine was hungry, it was getting hungrier every single quarter, and the planet was starting to respond in ways that the companies building these facilities had not fully planned for. The social and economic cost of this hunger was becoming impossible to ignore in the PGM region of the United States, which covers several major states. The arrival of AI data centers increased energy market costs so significantly that it translated to an additional $18 per month on household electricity bills in some counties. A March 2026 Brookings Institution report documented that electricity costs had risen 42% since 2019, significantly outpacing inflation. Utilities across the country requested $31 billion in rate hikes in 2025 alone. Goldman Sachs warned in February 2026 that data center-driven electricity demand would push core inflation higher in both 2026 and 2027. Ordinary families were effectively subsidizing the electricity bills of trillion-dollar corporations, and communities were starting to fight back in organized and legally effective ways. Research firm Data Center Watch found that between March and June of 2025, community opposition led to $98 billion worth of data center projects being blocked or delayed. People in Memphis, Tennessee showed up in numbers to protest plans to use gas turbines to power a data center. Local authorities in Virginia and Ireland were pushing back against permitting for new facilities because the grid could not absorb the load. The model was cracking from the pressure of its own excess, and that was before quantum entered the equation. And then, just as this pressure was approaching a structural breaking point, quantum computing showed up and changed the equation in a way that nobody in the data center industry was fully prepared for. It did not knock on the door politely. It arrived and kicked the door clean off the hinges. Subscribe right now if you have not already, because the next section of this story is where it gets genuinely mind-bending, and you do not want to be the person who missed the moment the whole thing shifted. Here is what quantum computing actually is, explained clearly and without the physics lecture that usually puts people to sleep. Classical computers, the ones running inside every AI data center on the planet right now, work using bits. A bit is either a 0 or a 1. That is the total foundation of everything any classical computer has ever done or will ever do. Every calculation, every AI model training run, every search query processed in a data center, every stream of video you have ever watched online, all of it is built from enormous chains of zeros and ones, processed sequentially and step by step. Quantum computers are built on an entirely different physical foundation. They use something called qubits, and a qubit does not have to be a 0 or a 1. It can be both at the same time through a quantum mechanical phenomenon called superposition. And when you connect multiple qubits together through a process called entanglement, the computational power does not add up the way classical computing does. It multiplies exponentially with every qubit added to the system. A 50-qubit quantum computer is not 50 times more powerful than a classical processor at exploring a complex solution space. It is simultaneously exploring 2 to the power of 50 possible states, which is over 1 quadrillion states all at once. For certain classes of problems, specifically the kinds of optimization and simulation problems that sit at the very core of AI model training, of drug discovery, and of materials science, this represents a gap in raw capability that has no historical parallel in the history of computing technology. And the practical demonstration of this gap is the moment where the story of AI data centers begins to fall apart in a very concrete and measurable way. Google's Willow quantum chip solved a specific benchmark computational problem in a matter of minutes that would have taken a conventional classical supercomputer 10,000 years to complete. Not 10 years, not 100 years, 10,000 years. And just as significantly, Google's Willow simultaneously demonstrated that it could achieve below-threshold error rates while scaling up the number of qubits, which means it solved what engineers had considered the second greatest obstacle in quantum computing at the exact same time. It was shattering performance records. Google's CEO Sundar Pichai stated publicly and with confidence that the company is optimistic practical quantum workloads will emerge within 5 years. That is not a vague hedge. That is a timeline backed by demonstrated results from a real machine. Like and subscribe right here because the implications of this single benchmark are staggering and they cascade into territory that the mainstream press is still not connecting the dots on. Google was not alone in the race. In February 2025, Microsoft revealed its Majorana 1 chip, which takes a fundamentally different architectural approach from anything else currently in the quantum computing field. rather than using superconducting qubits, the standard approach that almost every other quantum program has pursued. Microsoft's Majorana 1 is built on a completely new class of materials called a topoconductor, and it generates quantum states using exotic particles called Majorana zero modes, which were theorized in physics for decades but only recently engineered into a controllable form that can function inside a real processor. The practical advantage of this approach is significant. Topological qubits are far more stable and resistant to environmental interference than conventional qubits, and stability is the single biggest engineering obstacle in quantum computing. Every quantum system built so far loses its quantum state almost immediately upon interacting with its environment, requiring massive error correction overhead that eats up most of the theoretical computational advantage. Microsoft's topological approach attacks this problem at the materials level rather than the error correction software level. Microsoft's roadmap projects that this architecture can eventually scale to 1 million qubits on a single chip, and Microsoft projected that commercial quantum computers will be operating inside data centers by 2029, running calculations that classical machines simply cannot perform, full stop. Amazon was not sitting out this race either. In February 2025, AWS unveiled its Ocelot quantum chip using what is called a cat-qubit architecture, and Amazon's researchers claimed this design could reduce the resources required for quantum error correction by up to 90%. Error correction overhead is the main reason building a practical quantum computer has been so hard and so expensive. A 90% reduction in that overhead is not a marginal improvement. It is a potential step change in the economic and engineering feasibility of the whole enterprise. IBM, at its 2025 Quantum Developer Conference, announced that it expects verified quantum advantage by the end of 2026 and fault-tolerant quantum computing by 2029. In the space of a few months, every major technology company on the planet essentially confirmed simultaneously that the quantum era was not a distant theoretical possibility. It was an engineering deadline with a date attached and a roadmap behind it, and that changes the strategic calculation for everyone who has bet trillions on the current model. Now here is where most coverage completely loses the thread of what this actually means, and I want to make sure you understand what is genuinely happening beneath the announcements. The story is not that quantum computers are going to instantly replace classical computers and switch off every AI data center on the planet next year. The real story is strategically far more consequential and far more dangerous to the companies that have made trillion-dollar bets on the current infrastructure model. The real story is that quantum computing is about to render the foundational economic logic of the current AI data center model structurally inefficient, and in the technology industry, when your model becomes structurally inefficient against a superior alternative, what follows is not a gradual fade. What follows is a collapse of the investment thesis and a scramble to reposition. Go ahead and drop a like right now, because the next part is the analysis nobody in the financial press is putting plainly on the table. Here is the core problem with the current AI data center model, stated as plainly as possible: training a large language model or a frontier AI system requires running billions, sometimes trillions of mathematical operations across thousands of GPUs simultaneously for weeks or even months at a time. The reason this requires so much hardware and so much electricity is not because building AI is inherently a power-hungry activity. It is because classical computing is fundamentally brute force in its approach to the optimization problems at the core of AI training. It tries enormous numbers of parameter combinations and configurations sequentially until it converges on a good enough solution. This is a product of the architecture of classical computing, not an inherent property of intelligence or learning. The World Economic Forum, in direct published analysis of the quantum and AI intersection, described quantum computing as offering a path to dramatically reducing the energy and physical footprint per unit of AI work performed. A quantum processor operating at near absolute zero, using superconducting materials with no electrical resistance at the processing level, generates no heat in its core computational elements. The multi-billion-dollar cooling infrastructure that defines every major AI data center in the world today exists because GPU chips burn through massive amounts of electrical energy and turn most of it into heat. That is not a cooling engineering problem. It is a classical computing physics problem. Quantum does not have that problem in the same way. The numbers supporting the transition are already appearing in serious institutional analysis. S&P Global's research noted that the quantum computing market had projected 2025 revenues of $2.5 billion, but that global investment in quantum technology had already surpassed $55 billion in 2025 alone, when investment exceeds current revenue by more than 20 times in a technology sector. It signals that the largest and most informed capital allocators in the world believe commercial deployment is close enough to justify paying a significant premium for early positioning. UBS analysts published an analysis in early 2026 noting the industry is approaching a machine that can solve in 200 seconds a problem that would take a classical supercomputer 10,000 years. 200 seconds versus 10,000 years is not a performance differential. It is a paradigm boundary. The old model does not compete across a gap of that magnitude. It gets replaced. NVIDIA, the single company that has benefited most from the AI data center boom, has been watching all of this with extreme attention. Jensen Huang said at the start of 2025 that practical quantum computing was 15 to 30 years away, a statement that briefly caused quantum computing stock prices to crater across the board. But by late 2025, NVIDIA had launched NVLink, a platform directly connecting quantum processors and GPU supercomputers. With 40 petaflops of AI performance and a GPU to quantum processor throughput of 400 gigabits per second at a latency of less than 4 microseconds, NVIDIA also released its Q2Q quantum classical platform and introduced the Ising family of open source AI models specifically designed to manage quantum hardware error correction. More than 12 supercomputing centers and national research institutions across Asia and Europe adopted NVLink within months of its launch. NVIDIA is not betting against quantum computing. NVIDIA is building the infrastructure layer of the quantum classical hybrid era. That is what NVIDIA has always done. It identifies where the next dominant compute paradigm is forming and makes sure its technology sits at the center of it. Hit like and subscribe right now, because if you are following the technology industry, this strategic repositioning from the company that has been the biggest winner of the classical AI era is the signal that should be telling you everything. The architecture solidifying across the industry right now is hybrid quantum classical computing. Classical GPUs and CPUs handle high-volume everyday processing, data storage, and simpler AI inference. Quantum processors step in for the computationally hardest optimization and simulation problems. The exact workloads that currently consume the most energy and the most time in AI development. IBM is already running quantum computers next to classical supercomputers in operational hybrid configurations. Microsoft is engineering the Majorana 1 architecture to integrate into standard data center rack footprints. OData's 2025 industry report projected that by 2032, 5% of Tier 4 data centers will host quantum coprocessors for research and enterprise workloads. The language analysts are now using to describe 2026 is the language of deployment timelines and commercial verification, not research milestones. The transition from quantum as a lab curiosity to quantum as infrastructure has started. There is one more critical dimension to this story that deserves direct attention: the same quantum capability that makes classical AI infrastructure structurally inefficient for training also threatens to break the cryptographic security layer protecting every data center on Earth. The encryption systems that secure banking, government communications, medical records, and corporate intellectual property are built on mathematical problems that classical computers cannot crack in any practical time frame. Shear's quantum algorithm can factor the large numbers underlying those cryptographic systems exponentially faster than any classical machine. The moment a sufficiently large fault-tolerant quantum computer becomes operational, every system still using current public key cryptography standards becomes potentially vulnerable. The National Institute of Standards and Technology finalized its first post-quantum cryptographic standards in 2024 specifically because the security and intelligence communities recognized the timeline for quantum-capable decryption was compressing faster than public forecasts had acknowledged, transitioning the cryptographic infrastructure of a modern hyperscale data center to quantum-resistant standards is a multi-year, multi-billion-dollar undertaking. Companies that have been focused entirely on scaling GPU capacity have been deprioritizing this migration, and the window available to complete that migration before commercially viable quantum machines arrive is now measurably shorter than most public planning documents assumed even 2 years ago. This is the complete picture of what quantum just did to AI data centers. It demonstrated capabilities that make the current model unsustainable from three distinct directions at once. First, from the energy direction, quantum offers orders of magnitude improvements in efficiency for the exact computations AI training most depends on, making the power-hungry GPU cluster model structurally wasteful at a moment when energy costs are already generating political backlash and economic harm to ordinary households. Second, from the raw computational direction, quantum processors can solve in minutes what classical supercomputers cannot solve in 10,000 years, which collapses the performance justification for continuing to scale classical AI infrastructure at current investment rates. And third, from the security direction, the cryptographic foundation protecting every data center on the planet is built on math that quantum computers will eventually break, requiring a complete and expensive rebuild of security infrastructure across the entire global technology industry simultaneously. The $1 trillion committed to AI data center infrastructure is not going to evaporate overnight. The buildings will continue operating. The GPUs will continue generating revenue while they run, but the strategic narrative that justified every single dollar of that investment has been fundamentally compromised. The world built those facilities on the assumption that classical GPU-based computing was the permanent and scalable architecture for AI at scale. Quantum just made that assumption wrong in a way that cannot be talked around or delayed indefinitely, and in the technology industry, when the foundational assumption underlying a $1 trillion investment turns out to be wrong, the consequences cascade fast and they move faster than the people invested in the old model are ever comfortable admitting. Like and subscribe one final time right here because you are watching the early chapters of a transition that historians will record as one of the defining turning points in the history of computing. Every major technological transition in history has followed the same sequence. An assumption at the foundation of the old model turns out to be incorrect. A new technology demonstrates it can accomplish the same outcomes in a fundamentally more efficient way. The investment narrative shifts first, then the infrastructure follows. Mainframes gave way to personal computers. On-premise servers gave way to cloud computing. Feature phones gave way to smartphones. In every case, the companies that defined their entire strategy around the old model paid a severe price for being slow to recognize what was happening. The companies that understood the transition early and positioned at the intersection of the old and new not only survived but defined what came next. Quantum just demonstrated that the brute force classical computing model driving the largest infrastructure investment cycle in private sector history is not the final answer for AI at scale. It is an expensive, energy-intensive, and increasingly unsustainable interim solution. The final answer is being built right now in engineering teams at Google, Microsoft, Amazon, and IBM, and in dozens of quantum hardware companies racing toward commercial deployment simultaneously from different technical directions. The quantum era of AI is not approaching on the horizon. It crossed the threshold. The trillion-dollar data center industry will look profoundly different on the other side of this transition, and the only real question left is which companies and which people understood what was happening soon enough to be positioned correctly. If this video helped you see something that the mainstream technology press is still missing, hit like, hit subscribe. and share this with one person who needs to understand what is actually happening right now, because the next chapter of this story is going to move even faster than this one did.